Okay, I think we have arrived upon our start time. So I'm going to go ahead and welcome everyone to our first ever Saga TED Talk. Certainly the first of 2021, but it is the first ever. We're actually really hoping that this is going to be the first of a sequence of these. And some of these down the road, you might very well get involved in. A couple of quick items, logistical items. One is that you can probably already see we're going to record this session. So if for any reason you don't feel comfortable being on video during this, feel free to turn your video off. I'm also going to mute everybody in a moment as we start. And so without further ado, I want to introduce to you all, if you haven't got a chance to meet this guy yet, I want to introduce you to Sean Kelly, who is going to be leading our first TED Talk. So Sean, I'm going to turn the mic over to you.
Thanks so much, Chris. Hello, everyone. Thank you for joining us this afternoon or this evening, depending on where you are. The title of my talk is A Brief History of Time Since Turing. An alternative title might have been A Brief History of the Digital Computer, but since we've all seen The Imitation Game and we all adore Benedict Cumberbatch, I felt it was okay to write his draft a little. So computer engineering, like most kinds of engineering, is just chock full of jargon and acronyms, and some of those I would like to demystify today. I'd also like to the fellows in attendance today to leave with a better understanding of what a career in engineering looks like, what kind of skills you develop, and something of the joy of the craft, especially the craft of software engineering, which is what I do. So Turing was a mathematician who, because of his seminal contributions, is known as the father of theoretical computer science. In 1936, Turing wasn't really thinking about the computer per se, but instead he was thinking about the so-called Entscheidungsproblem, which was one of the 23 problems published by Hilbert in 1900. Hilbert is another famous mathematician. This list represented a sort of call to action for the new century for mathematicians everywhere. It's also known as the halting problem, so I don't have to butcher the German pronunciation again. Its statement goes something along the lines of, given a computer program and a set of inputs, is it possible to determine, which is to say, is it possible to construct an algorithm to determine whether the program terminates or it runs forever? So that's the halting problem. It's one of the first examples of a decidability problem. Now, Turing was able to prove the answer to the halting problem, and it was a resounding no. But more importantly, for the purpose of this talk, as part of the proof, he described a machine that's sort of pictured in the graphic that was a type of computer now known as the Turing machine, and its execution of a program, which is represented in the diagram with the tape, consisting of symbols on a tape that was outside of this computing machine. The computer can move the tape forward and backwards to read symbols. It can store intermediate results by writing back to the tape, but beyond that, it's a fairly simple device. Now, the thing to take away from the graphic is that the tape, which is to say the program, and the computer, the machine, are independent things. So in 1936, Turing introduced to the world the idea of a stored program computer. Now, this may not seem like a revolutionary advance to us, but up until this point, computing machines were single purpose. So from programmable looms in the early 1800s to the 1890s use of a census tabulator, which read tabulated data from census takers' punch cards and computed sums, through Turing's own pioneering work on the electromechanical bomb device used to decode Enigma ciphers at Bletchley Park during World War II. This is how automation worked until, dun, 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 someone invented the iPhone. Seriously, about a decade after 1936, the 1936 paper, general purpose computers implementing Turing's stored program concept began to appear. Turing's own implementation was not the first, but it was one of the first, and he was credited by such greats as von Neumann for the idea. And just to drive the point home, until Turing's idea, every app would have to be designed alongside its special purpose, one-of-a-kind phone. So there was no separation between hardware and software. So now, together, we're going to learn to count. Now, why do we want to do that? You'll just have to bear with me for a few slides. It'll all become clear. So before we learn to count, let's spend a slide on how not to count. One of the early counting systems was introduced by the Romans. I think the Roman system is unique in that it has survived until the modern day in places like clock faces and awesome video games like Skyrim, which is Elder Scrolls V. A couple of things to notice about Roman numerals is that the symbols are not equally spaced on the number line, 1, 5, 10, 50, 100, 500, and 1,000. The other thing to notice is that no matter where the symbols show up, they always have the same value. Now, the Romans would certainly argue that adding Roman numerals is easy. You just smash all the symbols together and then repeatedly apply a couple of rules like BB is X. The rub sort of lies with how to multiply and divide Roman numerals. And I found the quote, which I'll just read from the Wikipedia article on Roman arithmetic. If anyone can figure out how to do division, I'd be pleased to hear from you. This sounds like something from Hitchhiker's Guide to the Galaxy. So clearly Roman numerals was not going to survive as our primary way of doing even arithmetic. Now, before we move on, I want to highlight that the barrel of apples we're going to count and recount in the next few slides never changes. There's always the same number of apples, irrespective of how we choose to label the number. So next, we're going to learn to count like Muhammad ibn Musa al-Khwarizmi, the Persian polymath who invented the positional number system around Common Era 760. The thing to notice about positional numbers is that the symbol and its position define its value. So for example, the 3 in 324 apples has a value 300, or 3 times 10 to the second power, by virtue of its position in the second column, where I started counting the columns from 0. Another important thing to highlight is the invention of al-Khwarizmi's number system of the number 0. Without a number like 0, 304, for example, would collapse to 34 and the system would fall apart. Now, it was no accident that al-Khwarizmi identified 10 symbols in designing his number system. 10, of course, is the number of digits that we have on our two hands. However, what if positional numbers were invented by an octopus? And if you guys have seen My Octopus Teacher, highly recommend it. You can see how this statement could possibly be true. The natural number of symbols would be 8 in this case, and each position in the number would correspond to a power of 8. So our 324 apples would look like 504 apples in base 8 or in octal numbers. We've not changed the number of apples, we've just changed the way we express this quantity. Finally, we can imagine taking this to the so-called dolphin limit, which is base 2, 1 for each flipper. It's also known as binary, and a binary digit is called a bit. There are still 324 apples in the barrel, but I would label this as 1010000100 if I learned to count like a dolphin. So for fans of Flight of the Conchords, the robot's binary solo hopefully has taken on new meaning. So now that we know what binary is, let's talk hardware. So electronic components that make up a modern digital computer operate on discrete signals. You can think of digital signals as being like a light bulb with an on or off switch. The on state corresponds to the bit having value 1. The off state corresponds to the bit having value 0. Deep down inside, most of the subcomponents are of this said computer, or digital circuits rather, are intrinsically analog. And an analog component is analogous to a light bulb on a dimmer switch, where the signals can assume any value between 0 and some maximum value. So why do digitals count in binary? Why do digital computers count in binary? So my last slide posed this question, to which I answered because they are made up of components that expect digital signals. And this is a bit of a cop-out. There are lots of reasons to prefer digital signals, of which I will mention 2. And if you want more, you can follow up with our own Krista Marks, who designed digital electronics in a past life, or for that matter, our own Tom Fishaber or our own Jeff Ward, 2 more electrical engineers on the product team. A digital signal is the presence or absence of a voltage. You can see in the time series on the left that the signal is accompanied by bumps and wiggles. We call this noise or electronic noise. The moral of the story is it would have to bump and wiggle a lot for a 0 to turn into a 1. So it is in this sense that we say that digital is less susceptible to noise. Digital signals also can be repeated with a very simple device called a relay, shown here in the middle as the middle component on this cartoon telegraph line, which predates the computer by decades. Analog signals change in both frequency and in amplitude as they transmit down a wire. So figuring out what number you were what the original analog value was is much harder to do. Okay, a digital computer is nothing more than a bunch of binary numbers loaded into a memory and a mapping from these numbers to a set of operations that can be executed on the CPU. So there's an operation, for example, for adding 2 binary numbers, for subtracting 2 binary numbers, for reading a memory location, for writing to that memory location, to jump ahead on the program or to jump back. This should sound very familiar because it's exactly the machine that Turing dreamed up in his 1936 paper that predated the invention of this machine by 50 years. The owl meme is to acknowledge the fact that I skipped a bit, which is to say about 99% of digital electronics, so I could get to the good stuff, which of course is software. We made it to code. So on the left hand side of this graphic, I have written a simple piece of assembly code that prints the words "Hello World" in a terminal. This is the program "Hello World" that every single computer programmer in the universe writes first. In whatever language you're learning, this is the first program you write. So in several decades of working as a professional software engineer, I am happy to say that this is the first assembler that I have ever written. Assembly code is one step removed from writing code in binary and loading it into the computer 1 bit at a time. In fact, it's just shorthand for instructions that can be expressed as binary. The translation of this shorthand used to be done by hand. Now it's done by a program called an assembler. So just following this back sort of chicken and egg wise till you get to the beginning, the very first assembler had to be written by entering binary numbers into a computer by hand. The problem with assembler is that it is extremely low level. It sits at the so-called hardware-software interface, which is a problem because Intel makes hardware, AMD makes hardware, Apple makes hardware, Xilinx makes hardware. Since assembler targets specific hardware and specific instructions that are associated with that hardware, you have to write specialized assembler for every vendor. So I wrote this particular bit of assembler for the 64-bit architecture that runs on my Linux machine, x86_64. BC is before compilers. Okay, 1952, we're making progress. Ushered in the age of compilers. The first commercial compiler was Fortran, the Fortran compiler from IBM. Fortran stands for, is a computer programming language that stands for Formula Translator. Compilers pushed the job of writing code that would actually run on different architectures to the compiler implementers, leaving the rest of us software engineers blissfully free to write once and run anywhere. The often unspoken truth is that this still doesn't work today, which is to say, it's very frequent that we run into a problem of my software doesn't run the same thing on my iPad as it does in the same way on my iPad as it does on my Safari browser on my desktop. We call this problem platform dependence, and it's the bane of all mobile web programmers for sure. The program on display here is the same Hello World program that we wrote in assembly, but it's written instead in a high-level language called C. Now, compilers are the program that essentially read this high-level programming language and emit low-level assembly code that can be assembled down to whatever architecture you're interested in. Compilers take time to do their job and spit out their code, so this explains why software engineers are addicted to coffee. So what the product engineering team at Saga does is called application programming. More specifically, we create applications that run inside a web browser. So this is also known as programming for the mobile web. I'm going to show one such program called Bounce. Anyone who has interviewed with me in the past decade or so has seen Bounce because it's part of my interview. We start with an innocent-looking red ball at the bottom of a box and a provocatively named routine called Bounce. There are other unimportant parts of the program that I haven't shown, and I tell the developer that I'm working with to ignore. What I do tell them, however, is every 100 milliseconds or so, their routine called Bounce gets called and that they should do something interesting. Now, this is the best part of the interview. What I do next is leave and go get some coffee, which is to say I service my addiction to coffee that I developed during the age of compilers. I'm showing you this program because I want you to go back to your students and tell them how fun it is to be a software engineer and that you have the secret that will help them ace their interview. More importantly than that, I want to make the point that software engineering requires math. This is my two-line solution to the Bounce problem. Now, you're like, wait a minute, there's more than 2 lines here. But really, all of the lines above the Bounce routine are just constants that I'm using to make the implementation of the formula that's expressed mathematically more readable as code. So that formula describes an exponentially damped sinusoid, which is to say, a sinusoid that's oscillating with a frequency nu and has a decay constant tau. Without the exponential, the ball would just bounce and bounce and bounce. Without the sinusoid, the ball wouldn't bounce at all. Interestingly enough, the motion of the ball has nothing to do with physics or a realistic model of the physical ball. That would involve all sorts of things: energy loss, deformation, frictional heating, gravity, wind resistance. But as long as you're in the matrix, say a video game, it doesn't really matter what chicken tastes like as long as you think it's juicy and delicious. Which is to say, a lot of the work we do as software engineers is to take things that are models of reality that are more performant or more easily expressed and implement them in code. Physics, we just push physics to the side. So we're getting close to the end now. I'll say that for coders, the sky is the limit when it comes to math. This graphic shows the first use of vector calculus I saw outside of a textbook. And it happened a few years back when the second renaissance in artificial neural nets began. Backpropagation is the name of the algorithm expressed in these scary-looking formula. And backprop is the algorithm that's essential to training neural networks. These equations are required learning for experts in pattern recognition. So not all software engineering requires graduate level sophistication in math, but some certainly does. So it's in this sense that I say that the sky is the limit. And I will close my talk with a question, which is, how close are we? On the left-hand panel, you see the 2016 game between the world champion ninth Dan Go player, Tang Weijing, and the neural net based computation engine AlphaGo by Google. Of course, the machine won. And so the question I leave you is, how close are we? I will just drop this right before we close, which is to say, that would be an interesting question to have answered by maybe a future TEDx talk in this very format. And I can think of just the person, Brent. And with that, I'll take questions.
So yes, we're going to open it up for questions now. So please, anybody, questions on any part of what Sean shared with us today, feel free to enter them into the chat, and I'll do my best to moderate. I see some folks populating. Sean, can I just start with a very general question? Like, when was the first time that you just absolutely geeked out over this field and decided I'm jumping in with all of myself? What was it?
That's a good question, Chris. So my background is actually in physics. So I was an academic physicist for 10 years before I even started doing software engineering. Not started doing software, just before I became joined industry and joined the dark side, so to speak. But I was 2 years into grad school, pushing a pencil for a living, convinced I was going to be the next Albert Einstein, when I decided I actually didn't like breaking my mechanical pencil 12 times a day, and I much preferred building things. So at that point, I joined an experiment, and as an experimental physicist, you basically learn to you have to build experiments. You're either a hardware or a software engineer, and I became a software engineer. And as soon as I started creating, that was it. I was off to the races. But an interesting, an aside to this is that you don't have to start when you're 12. It helps, but you don't have to. You can start when you're 25, which is essentially when I started.
Gotcha. So on that same pathway here, is there a typical path that a software engineer would take?
Yes. A typical path would be a 4-year CS degree or a EECS degree, electrical and computer engineering. The thing that I like to highlight in terms of guidance, unsolicited advice to young would-be software engineers is everyone takes the same classes. So if you plan on being a software engineer, start building software as soon as you can. Build a website to scrape your favorite scores from ESPN and plop them up on a screen for you to look at. Build a game, do some modding for Minecraft if you're, on the 8 to 12 age group. But just start coding as soon as you can, because every little bit helps. And the way you discriminate yourself from your fellows is by having actually written and implemented something interesting.
I love it. And this one's from Yazi. What is the most important math class for computer science?
That's a very good question. Thinking. Well, I'm going to say probably vector calc, but only through the prism of wanting to pick up and do machine learning. Discrete math, certainly. Discrete math and computational thinking are both sort of classes that you'll be exposed as part of a vanilla CS degree. But vector calc certainly makes it easy to read the formula of the variety that I showed on that last slide.
Excellent. This is from Mr. Bennett. What kind of software is Saga writing?
So we write applications. So we wrote the tutoring platform, which is to say the integrated synchronized whiteboard plus the audio video conferencing integrated, the chat. So we basically write front end and back end software to service Saga's digital learning platform. And we will continue to write software that does just that, which is to say we have plans for a training portal, we have plans for a practice tool. Again, sky's the limit, but all in service of Saga's mission.
Excellent. Here's another one in terms of getting an early start. What is a good programming language to start with if you're new at this?
If you're very new, I would start in Ruby. It's a gentle syntax. It's easy to learn. It's fairly sophisticated. It's not compiled, so you don't have to wait around for. It's an interpreted language, so you get instant feedback. Um, but what you're going to learn very quickly is it's hard to do very interesting things in Ruby. You can add up all the numbers between 1 and 1,000 as your first program, but if you want to make a ball bounce on a screen, you're going to have to implement in the language of the web, which is JavaScript. So JavaScript's a little bit more of a hit by the ugly stick programming language because of its genesis, 2 decades ago in web browsers. But a variant called TypeScript that comes out of Microsoft is slightly prettier, and it's a typed language. It's easier syntactically, and it's easier to reason about. That's where I would start with Ruby just to get your feet wet, and then move on to JavaScript and build me a web page suitable for Mordor.
Connected to that, what languages did you all use for the Woot Tutor platform?
So Woot Tutor is it's actually we have 2 front end languages that we make primary use of. One is Hax, and the other is TypeScript. And these are both, and then some JavaScript. But the thing that these languages all have in common is that they so-called transpile to JavaScript. So compiling and transpiling are sort of similar, but they're different in the sense that the transpilation process doesn't generate machine code. It generates a different language. So it's like translating from French to German. So if you like to program in Hax, say, you can write in Hax and have it spit out JavaScript, and that'll run inside a web browser. So that's on the front end. On the back end, again, Ruby, TypeScript, Hax. So those are the 3 big ones, I guess.
Excellent. Here's a different one. This is from Jay. What's the best thing you learned as a young software engineer?
How to debug. Absolutely. How to debug, which is to say, you think that, writing a computer program is about sitting in front of a keyboard and typing this perfect code. That's really not how it works. You make many, many mistakes along the way. And the first time you run your program, it blows up in your face. And you spend, a good half of your cycles as a software engineer trying to figure out why your program doesn't work. And so there's tricks and tips and tools that really help make debugging a joy. So that was probably, I learned that in the trenches on a physics experiment, debugging an early distributed data acquisition for a big physics experiment out in New York. So that was trial by fire, but that was the most important thing.
Excellent. So one of the things that we celebrate a lot is the diversity in age and experience and different careers that people have had. But if you didn't start as a software engineer, you're mid-career somewhere, can you still become one?
Absolutely. So what I would suggest is, they have these schools out there now. They're called, one of them is called the Turing School. And they are sort of boot camps for programmers. 6 months, 6 to 12 months of intensive programming. Now, the truth of the matter is you can't cram a 4-year degree into 6 months, but what you can do is get yourself trained up enough to actually get a foot in the door and do something useful for some company somewhere. And then you do just a ton of on-the-job learning. So, again, my path was not traditional, but I really did learn everything I know about computer science on my own. I never took a CS class in college. So yes, you can absolutely start over. And actually, some of the people we see coming out of the Turing schools and the code academies are what I would call path backers. And these are often, male and female engineers that have, often female, that have taken time off to start a family and then want to come back into the workforce, and they've taken the Turing, maybe they have some previous technical training or some expertise in an unrelated field, but a technical field. They come in, they take the boot camp, and then they have the maturity and the sophistication of someone who's been out in the workforce before, those are appealing from the perspective of a hiring manager.
Sean, I'm going to go rogue for this last question and insert my own here. If you struggle to understand some of what you shared today, like I did, because I don't have this background, and you want to go out and you want to get a book to start, can you recommend, what would the first book be that we should buy? Jump on Amazon that will give us that great entry point.
Boy, that's a tough one. Well, so this talk was based on a book called Code that one of my engineers, Adam Holt, handed to me. Code is not really about software as much as it is about the background that leads you to understand that software is nothing more special than a bunch of instructions that are run by a highly intelligent instruction-based machine. So that's a great one just to get your head around everything in this talk. You'll find a lot of a lot of material is drawn from that. In terms of general purpose programming, I would just what I would stay away from is the 500 page telephone size books on like Ruby in 21 days. That's just that you'll fall over from boredom before you get through the first 10 pages. So I would find a slim monograph, and I'll give it some thought actually. There's one book on algorithms that I really enjoy. It's called Algorithms in Haskell, and I like it because it's incredibly terse. It's like 90 pages long. So let me get back to you on that. I will happy to follow up with an actual recommendation and some references.
If you like RPN calculators, you might like Haskell.
Yeah, Haskell's a tough one to love.
On that note, I see that we're at time. We're a little over. I want to thank you, Sean, for leading the way and piloting our first TED Talk, for the time that you're spending with us and sharing your history, your knowledge, your skills. Really, really appreciate it. To all of you who joined this evening, late afternoon, thank you for just making this a wonderful first community event. So we wish you all a wonderful evening, and we'll see you on our next TED Talk.
Thanks so much, everyone. Bye-bye.